Alright, question 5 reads Cecil approaches a source emitting sound with the frequency of 431,1 hertz. Alright, question 5a asks how fast does Cecil need to move in order to observe a frequency that is 20% higher? Okay, so this is how we're going to approach this question. Okay, question 5a. Well, they want to know how fast does it need to move to observe a frequency that is 20% higher than the original. So let's take our original to be 1, and we want to know how fast does it need to move to observe a frequency that is 20% higher. Alright, so 1.2. So therefore, f of L is going to equal 1, 2 times f of s. Alright, that's what we want to know. Alright, or that's at least the distinction that we can make. The Doppler effect formula we know is FL is equal to V plus minus VL over V plus minus Vs, all brackets, times that F of S. Alright, now we know what FL is equal to, so we can put that in there as 1, 2 Fs. Alright, is equal to it's V plus the velocity of the listener. We need to know how fast does he need to move. Alright, all over the sound source is stationary, so all over just V, alright, times f of s. Alright, so what we can do here is we can get rid of f of s on this side. That cancels. And then we can go ahead and do the same thing over here. Alright, then we got 1, 2 is equal to V over V plus VL over V. Alright, we can see that though over here, so we know that this is equal to 1. Alright, this is equal to 1. Therefore, we can take over on this side. Alright, 1, 2 minus 1 is equal to VL, assuming that the speed of sound is 340 meters per second over 340. We know this is going to equal 0.2, equals now VL over 340. We multiply this side by 340 on this side as well as on this side, and therefore we get the velocity of the listener, or Cecil, to be equal to 68 meters per second. Alright, perfect. That was quite a simple question. Okay, just note that they taking the original frequency to be 1. So we want to know how fast does it need to move to observe a frequency that is 20% greater than that. Alright, so then we have to take 1 times 0.2 to get 1.2 to find out how fast he would need to move at 20%. How fast he would need to move to hear a frequency 20% greater than the original one. Okay, so we're going to go on to question 5b now. I'm just going to clear the screen. I just go straight to B. Alright, let's go have a look at B's question. B's question was, if he passes the source at this speed, what frequency will he measure when he is moving away? Alright, so therefore, okay, the frequency calculated if he's moving away, we know that that now changes now to V minus VL all over V times f of s. Alright, now we want to know how much is he going to measure, assuming that V is equal to 340 meters per second. Alright, we know now that this is f of L. Alright, and we could just plug in here 340. Alright, 340 minus let's see, minus, we worked it out to be 68 meters per second all over 340. And let's just check here. It said that source emitting sound of 437,1. Alright, so we can bracket this. which is 437.1 hertz. All right, multiply that. Okay, if we punch that in on our calculator, we get that the frequency that he will measure, or f of L, is equal to 349.7 hertz. Okay, and that's what he measures, alright, when he's moving away from the sound source. Let's have a look at the third question, or question 5C at least. What is a practical means of achieving this speed? Well, we can make the speed, which is 68 meters per second, make it a little bit more appealing and striking. All right, if we decided to convert it to kilometers per hour, so if we take 68, all right, and we multiply that by the conversion, which will be multiplied by 3,6, all right, we get that to be equal to, all right, 68 times 3.6, which is the conversion, to be equal to 244.8 kilometers per hour. All right, and now once we get that, we can see 244.8 kilometers per hour. A practical means of reaching this speed would either be, all right, so this speed could only be achieved, all right, in a high-speed train, or in a racing car. All right, or in a racing car. So that's the only way that Cecil could basically achieve this speed, okay? Because remember, the velocity of the listener was 68 meters per second, which we converted, so me and Cecil's basically traveling at 244.8 kilometers per hour. So there's no way he can run or walk or run, even crawl at that speed. You know, it's humanly impossible. So he could have been in a high-speed train approaching the sound source, or he could be in a racing car, or in a car, you know, because a normal car won't average 244.8 kilometers per hour. It'd have to be a racing car with a very, very strong engine, etc., etc., to achieve a speed of that magnitude. All right, 244.8 kilometers per hour. Okay, and that answers question C, and that concludes question number 5 of the exercise 6.1 of the Sciavula textbook.